So we're going to talk a little bit about drag now. Now, drag is that force that retards the motion of a vehicle. It's the summation of the pressure and the friction forces in the, I guess we could say X direction, but it's along that roll axis. Now, a couple things about drag. We're going to take a very high level, simple look at drag, same thing with lift. And we're really going to base it off of a dimensionless parameter. And so that dimensionless parameter, let's not use red, is what we call the coefficient of drag. So C sub D. So this is the coefficient of drag. We'll see this a lot. Now, the coefficient of drag has a fairly simple definition. So as we look at it, it's going to be the drag force. And then we have to normalize that drag force. And the way that we do that is we use this term for dynamic speed here, rho over 2 velocity squared. And then we multiply that by A, and I'm going to put a star in there. And so the A star, the reason I have A star in there is drag gets a little bit tricky because we have three main areas that we can use, and it all is going to depend on what we're looking at. And so the first one, the first version of A star could be frontal area, which would be A sub F. And actually, I should really have that, I should have that star down here because we're replacing that with these little subscripts. Okay, and so what's the frontal area? Well, that would be the area as seen from the stream. So if I had a cylinder here, and I have my stream coming this way, and in class, the example that I'd use is I'd hold out a pen and say, imagine, and you can hold out a pen and do this yourself, imagine the stream is flowing from your eyeballs to the pen, and so what do you see when you look at the pen? If you're looking directly on it, you don't see a cylinder, because from the stream, all you're going to see is a rectangle. Like I said, hold out your pen right now, take a look at it, you can see that. And so that would be the frontal area. You know, a sphere would look like a circle and everything like that. Where would you use the frontal area? Frontal area is good for thick, stubby bodies. And so this would be if you were calculating the wind force on a sign or a building. Actually, if you were calculating out the wind force on your car, which we'll do an example where we're calculating out the wind force on a car. A parachute, if you were calculating out how much drag a parachute's going to give you, and if you like to jump out of perfectly good working airplanes, one, you're crazy, but two, that is what you need as the drag force, and so you calculate it out based on that circle. The second one is what we call the planform area. Now, planform area is kind of neat, so that would be A sub P. So planform area is kind of like the frontal area, but it's the body seen from 90 degrees above the flow. So if we're looking at our pen and we just rotate it 90 degrees, the planform area of the pen would be that circle on the top. Planform area is really used for wide, flat bodies. The big ones being an airfoil, a hydrofoil, a spoiler. Those are all things that we use the planform area on. Now the third one is another interesting one. It's what we call the wetted area. Be A sub W. Now the wetted area, once again, think about it, fluids. Wetted has a meaning for fluids, and that's basically it's the area that's touching the fluid. Where would you use the wetted area? You'd use the wetted area mostly on ships below the waterline and blimps. Would be a couple of the biggest places where you would use the wetted area. By far, frontal area is going to make up probably, especially in your problems, is going to make up like 99% of the problems that we do. Planform area, for a lot of times you're not really looking at a lot of drag on these wide flat bodies, because typically these wide flat bodies are going to be your lift generation bodies, and they're really going to be generating a lot of lift, not so much in drag, but we're going to talk about how those things change here in the next couple lectures. And then the wetted area gets used a lot for, like I said, blimps and ships. Now, there are a lot of, I guess you should box this. There's only a couple equations that we're going to have for flight theory. That's one of the big ones. Now, as we look at it, there's quite a few things that go into making up your coefficient of drag. So the coefficient of drag is a function of a bunch of different things, and one of the biggest ones is probably shape. And then, Reynolds, Mach number, the Froude number, all have relations with the coefficient of drag. Now, Froude number is not something that we've gone over, but the Froude number is going to happen on things like underwater wings. It's a very specialized kind of thing. But also epsilon over L. So we've dealt with epsilon over D being the roughness ratio in our pipes. Well, epsilon over L is the roughness ratio for our wing. And as we'll talk a little bit later, this is going to have an effect on things. And if you're a golfer, we'll talk about that. It's going to be interesting. So let's just take a look at how these different things kind of influence what's going on. So once again, here's our pressure and shear stress distributions that we had, that we made up our forces from. And so if I look at it, you can see, I thought I put that on highlighter. We can see that in the x direction, all these guys contribute to that drag force. And then the drag force from the pressure is going to be all this area here. So everything else is going to contribute to the lift of the plane, or the lifting, or the airfoil or hydrofoil. And so what we have is the coefficient of drag can be broken up basically into these two huge components. Is we can look at what we call the friction drag, which is all the stuff from the shear stress. We have fluid pulling across it. There's going to be a lot going on with the shear stress, and so we have that. But then we also have the pressure stress, coefficient of drag of the pressure. Now this pressure drag, typically I'll refer to it as form drag. And the reason it's called form drag is it's very highly dependent on the shape. Because if you take a look at this, the more and more streamlined we make this, the closer we get to a flat plate, that pressure drag is going to drop off like crazy. And so it's really going to be the shape, or the form, is going to really drive that. So pressure drag, shape drag, form drag, all the same thing. All of those mean the same. And then the friction it's friction. It's just really, it is friction. So if we look at this, if we have a highly streamlined body, or we're flowing very slowly, friction is going to give you the majority of your drag. Because if this is highly streamlined, if it's basically a flat plate, there's not going to be a lot of shape drag, because it's just going to cut right through it. So most of it's going to be this shear stress drag. But if we start taking a look at it and making things fatter and fatter and fatter, you can see with this pressure pushing on it, you're going to have a lot of drag just from the shape. So let's take a look at a couple of pictures here from your books. This is kind of interesting. So all this is based on this guy right here, this little picture. The thickness versus the chord. Thickness would just be top to bottom. Chord is, as we talked about, the length from the leading edge to the trailing edge. Now, this starts out as a perfect sphere, and it just gets tapered and more tapered till it eventually becomes a flat plate. So what's interesting about this drawing, as you can see, we've got these curves in here, and I've got my coefficient of drag based on the frontal area, which would be AF, coefficient of drag based on the planform area. And so we're looking at the thickness ratio, T over C. So T over C of 0 would basically be a flat plate, and it's getting more and more round as we go. A T over C of 1, which means the thickness and the chord would be the same size, would just be a drag. Would just be a cylinder. And so the reason that I like bringing these up is basically for this top drawing here, and looking at the percentage of drag. And so along the x-axis here, we have the friction drag percentage. So at T over C being 0, that's a flat plate. And if I look at that, it's pretty much 100% of the drag is friction drag. And then if I go and I look at a T over C of 1, which is our cylinder. Wow, I can't spell this morning. Cylinder. If we look at it, 3% of the drag is friction drag. So that means 97% of it comes from that form drag. So this is just interesting kind of thing going up, wondering, okay, well, where do we have about the exact same amount of friction drag and pressure drag? Well, that would be at a T over C of about 1/4, which puts it about right here. And you can see that we're about equal amounts of friction and pressure drag. So that just shows you a little bit how that drag force is going to change depending on how streamlined it is and not. So in the next lecture, we'll go over and we'll talk a little bit about the Reynolds number, and then in following lectures, Mach number and whatnot. And what we're finally going to get to is, okay, we figured out, we know all this about drag, how do we overcome it?